This video covers how to approach Newton's second law problems with inclines. So here we have a mass on an incline that is a given angle theta off the horizontal axis. To simplify this problem, we assume that the y-axis is perpendicular to the incline and that the x-axis is parallel to the incline. This allows the acceleration of the object down the incline only to be in the x direction. This makes our calculations easier in the future. Alrighty, so we know that there's a weight force and a normal force acting on this object. It is apparent that the normal force acts on the y-axis, but the weight force is a little bit more difficult to break up into x and y components. So these are the x and the y components that we're looking for. To go about finding these, we can first look at this small angle between the surface and the weight force. We know that since there are two intersecting lines, that the opposite angles must be the same. We then can see that we made a small right angle here with the surface and the y component of the weight force. This small triangle has the same angles as the larger triangle. Alright, so we know that this angle at the top must be also equal to theta. We will then look at this triangle that is made up of the weight force and its x and y components. We can use trigonometry to see that the y component of the weight is actually equal to the weight times sine of theta, and the x component is equal to the weight times the cosine of theta. Now the reason why this is confusing is because at this point in the course we've typically associated the x component with cosine and the y component with sine. This is no longer true. So let's do an example. A 2 kilogram mass moves on an incline where the coefficient of kinetic friction is 0.3. Determine the acceleration of the mass as it slides down the incline. So since this is an incline problem, we know that we are going to reposition our usual coordinate system to be in line with the incline. And let's draw a free body diagram to analyze the forces acting on the block. So we have a normal force, we have a kinetic friction force that opposes the block's motion, and we have a weight force acting down. This weight force isn't in line with our coordinate system though, so we need to break it up into its components, like this. Take note that the y direction is mg cosine theta and the x direction is mg sine theta. Next, we will apply Newton's second law to the y direction. Okay, so we have a normal force acting up and the y component of the weight force is acting down. There's no acceleration in the y direction, so we can set this equal to 0. Next, we can apply Newton's second law to the x direction. We know that the x component of the weight force is acting in the positive direction, and the kinetic friction opposes the velocity. We then set this equal to the mass times the acceleration in the x direction. So there is a kinetic friction force acting in the x direction, so we must find what this force is equal to. We know that the kinetic friction force is equal to the coefficient of kinetic friction, which is 0.3, multiplied by the normal force, which is equal to mg cosine 60, which we found from the application of Newton's second law in the y direction. So now we have an equation for the kinetic friction force. So let's place this value into the x direction's Newton's second law equation. So we can then plug in our known values, and we see that the acceleration is equal to 7.2 meters per second squared.